Since 2018, Purdue Engineering Distinguished Lecture Series invites world-renowned faculty and professionals to engage in thought-provoking conversations about grand challenges and opportunities in their field. Besides presenting a lecture to faculty and students, they will also engage into a panel discussion at the end of the lecture. I'm happy right now to introduce Arvind Raman, John Edwardson, Dean of the College of Engineering, and Robert Adams, Professor of Mechanical Engineering.
Good afternoon. I'd like to add my warm welcome to all of you who are here today in person on this very cold day, and to everyone who's watching online as we live stream this event. I'm really delighted that we're kicking off this calendar year's Purdue Engineering Distinguished Lecturer Series with today's distinguished lecturer, who I have the honor to introduce shortly. Dr. Kristin Persson is the Daniel Taleb Distinguished Professor of Materials Science and Engineering at UC Berkeley, where she also concurrently holds a senior faculty scientist position at the Lawrence Berkeley National Labs. She is a world-renowned expert in atomistic computations and high-performance computing, really for the physics and chemistry of advanced materials used for energy production and storage. And she's really taken on many national and international leadership roles, and I'd like to tell you a little bit about them as well. From 2020 to 2024, she served as the director of the Molecular Foundry, which is one of only 5 U.S. nanoscale research centers. Now, those of you who have a chance to go to Berkeley will notice a very odd-shaped cantilevered building that's coming out of the hillside overlooking Strawberry Creek, right? And, well, that's the Molecular Foundry, if you ever want to know where to go. In addition, in 2011, she's really known internationally for having established the Materials Project, which has emerged as one of the most visible programs internationally that has addressed the goals of the Materials Genome Initiative. She served as the director of the project since its inception, and today, the Materials Project serves millions of materials data records every day, providing access to more than 500,000 registered users worldwide. In fact, in 2021, the Materials Project was recognized by the Department of Energy as an official public reusable research pure, in short, data source for materials data and design. For her tremendous leadership and technical achievements, Dr. Perrson has been significantly recognized. She received the DOE Secretary of Energy's Achievement Award twice, 2 awards from the TMS, the Cyril Stanley Smith Award and the Faculty Early Career Award. She was named in 2024 as the DOE Office of Science Distinguished Fellow. She's a member of the Royal Swedish Academy of Science, an MRS Fellow, AAAS Fellow, and an APS Fellow. Will you please join me in welcoming Dr. Persson to the stage?
Thank you so much for that very, very kind introduction. I'm quite humbled, and I'm really happy and excited to be here. This is a spectacular venue, and it's nice weather, too. I don't know what you're talking about, being cold. My talk today is going to be framed by the need for data-driven methodologies to accelerate materials design, but I will give a focus on materials synthesis specifically, so a bit of a deep dive into that. And I'm going to start out with this graph or this timeline that I borrowed from Matthias Scheffler, a dear colleague who's also very excited about data-driven methodologies. And we're phrasing the sort of trajectory of scientific discovery or paradigms of science, starting out with empirical, where you sort of make observations in nature. If you're Newton, you're seeing that apple falling from the tree, and you're going, ah, and then you see the apple falling from the tree again, and you go like, there's a pattern here. And if you know some math, you can now cast that apple falling from the tree and the velocity with which it hits the earth into an equation. So that's the second paradigm of science, when you don't have to watch it again to figure out where it's going to go. Now, some of those equations are hard to solve by hand, and you may need computers. So when the computers came around, suddenly we could solve more of those equations. For example, the Schrödinger equation, which tells us how matter behaves. Imagine now that I can amass enough data, either by simulations, by simulating the Schrödinger equation, or by doing these observations and cataloging them of nature and nature behavior, you can achieve the fourth paradigm of science, where we do data-driven. So we fit some sort of machine learning algorithm to all that data, and we're asking that algorithm to extend its predictions slightly outside or within its data set between data points, thinking that that's going to be sufficient or robust enough. And of course, that all depends on the amount of data you have and how systematic and robust it is. But that's where we're starting to see some of the innovation for material science today. And I'll be honest, all of my students who want to join my group today, and maybe in the last 5 years, they all start with, I want to do machine learning for material science. And I go, fantastic, you want to drive that nice Ferrari, I get it. I would like to do that too. But in order to do that, you're first going to have to produce the fuel being the data. Because in most cases in material science, we're not like the lucky people in traffic patterns or restaurant reviews where people give away their data for free. I like that restaurant. I did not like that restaurant. I hate that Netflix movie. I like another Netflix movie. People click on those like links everywhere and give off their sort of preferences for free. But in material science, every data point tends to be rather hard work, especially in the experimental side of things, where you have to produce, you have to synthesize a material. It has to be rather phase pure, or you can't assign the properties to that particular material. And then you have to characterize it, and then you have to write a paper, and then you have to put that data somewhere. So there's a lot of work. We get it, right? This is not easy. So that's where the fuel comes from. And you can't do machine learning without good data. I'm going to take a bit of a pause there, because some of our decision makers think that you can. That's the whole point of the data-driven paradigm. And the sadness of the whole thing is that in material science, we're actually poorer than in many others. For example, if you're lucky enough to be in protein business, the protein people had some vision. I think it was 1971 where Brookhaven started the protein data bank. And it took a few years, and I think the NIH had to put some rules and regulations in place for people actually to deposit their protein structures there. But now today we are seeing the benefits, right? When people are getting the Nobel Prize for inventing the algorithms, but they have to have that data to test on and to train on, or they wouldn't be able to get there. But all those years of hard work from people, that's sort of slightly, it underpins, but it's not maybe as recognized. So data and material science, when I was a graduate student back in Stockholm, you could probably hear my little accent. If I wanted data from materials, there was no internet. Well, it was just beginning. So I mean, I think I gamed on like somewhere in Switzerland. But if I wanted data from materials, I went to the trusted books of Landorlt and Bernstein. That if you look through Landorlt and Bernstein, I don't know if you have those books somewhere here, probably in some vault. You can find a couple of hundred elastic tensors. And if you go through the open literature, maybe you can find a few more. But the full elastic tensor requires a single crystal. It requires a lot of that really hard work to get. And I would also argue that it's not something you get a tremendous amount of recognition for. If you were to measure an elastic tensor for a single crystal material, would that get into Nature or Science? And I've said this to DOE program managers too, so not just to you guys. So my opinion is here, and that's why I put it in red, is that scientific data is mostly valued when it's tied to discovery, not just the data itself. So that's why you see higher numbers of data points for superconductivity and superconductors, because that is directly tied to an exciting discovery. If I find a high TC, I could be rich, or at least famous. And again, if you go back to something more fundamental, like the dielectric tensor, you're back in the hundreds, because again, it's not directly tied as much as more of a fundamental property. But these are so important. If we're truly going to do data-driven, we need these data points, and we need them not just computational ones. These are the gold standard data points that I test my Schrödinger equation predictions on and my then machine learning. So these are tremendously important. So computations did come to some degree to the rescue. In the early 2000s, we started doing what we call high-throughput computing of materials properties. So we could cast the Schrödinger equation, at least for ground state properties, into a framework where we could now calculate some materials properties much faster than what we could synthesize, characterize, and measure them. So that now became a vehicle for getting more data and getting it systematically. Whether you call it systematically right or wrong depends on which chemistry you're looking at. DFT certainly isn't entirely correct, but it is systematic. So to give you a little bit of one slide on the perspective, I was a graduate student back in Stockholm in 1996. I spent an entire year on calculating the phonon dispersion curves of tungsten. Why did it take me a whole year to do that? For those of you who have DFT people, you can probably get the same data in about a minute, maybe. Venture a guess, I would say so. Well, because I had to fit the pseudopotential, which most of the time you guys just take because it's there and it's nicely benchmarked, but they didn't exist back then. I had to fit the pseudopotential. I had to parallelize the plane wave code, and I just had the first linear response code for metallic elements that was given to me by a previous graduate student. So there was a lot of work underlying just that set of data. We now fast forward about 20 years, then you can see the change, right, and the availability of data. So on the materials project today, we have 150,000-ish, we add a few more here and there, inorganic materials and millions of associated calculated properties. For example, thousands of phonon dispersion curves, way past elements. There has been a paradigm change in the amount of data that we can now have, fundamental materials properties that we can use to design materials and at least get a little bit ahead of the game. So design materials, that's what we want to do, right? This is a plot out of I think a Scientific American article that I wrote together with Yerban Seder a few years ago, where they basically said, well, this is what we want to do, right? We want to go away from the Edisonian approach. And let's put Thomas Edison up there when we're talking about him, which is sort of baptized after the guy who, I think it took him 3 years to test every single carbon he could come up with because he was convinced that it was going to be carbon that went into his little filament in the light bulb. And there are a couple of take-home messages from that, right? First of all, he was convinced. He used his intuition that it was going to be carbon. Today, we call that prejudice, bias. And indeed it was, because carbon did not end up being the best element. It was tungsten, going back to tungsten. It was a Hungarian group, I think a decade later, that discovered tungsten. So bias, limited time, caused this sort of Edison approach of trial and error, okay, this is the best one, I'm going to go with that one out of my limited amount of time. So can we do better? And this is where I want to put up, Tony Stark. I would love to be Tony Stark. If you remember the first Iron Man movie, I think it's the first one, where actually I want Jarvis. I don't want Tony Stark. I want Jarvis because Jarvis is the cool computer that basically has all the data, simulates everything that Tony Stark wants him to do, and literally in 30 seconds he has a new material, and I think it's tested for biological compatibility. That's pretty tall order, but that's what we want. We want simulated best candidates. Don't stick with the carbon. Go outside of your comfort zone. Try whatever is in the periodic table and give a smaller subset of possible materials to your experimental colleagues, keep working with them, and eventually, maybe, hopefully, you come up with a better material, and that certainly uses more information than just, I have a pretty good feeling it's going to be carbon. So at this point in my talk, or somewhere around here, I feel like I'm becoming a little preachy. Like, yeah, this sounds great. Yeah, sure. What does she really have to like, is this really true? Can this really work? So I am really happy to say that I have at least one point of success, a material that I've followed all the way from predictions to commercial success. And so that's why I feel comfortable talking about it. So in 2004, 2005, I was hired as part of a consulting team to come up with a better cathode in these little alkaline batteries, the Duracell batteries. And for those who know, they usually contain manganese dioxide. Now, manganese dioxide is literally dirt. It's really cheap. You can dig it out of the ground, no problem. But Duracell was worried that, okay, it's really cheap, it's been around forever. What if there's something better out there? We should know about it before our competitors do. So they've heard about people doing screening computationally, and they had a large underutilized cluster somewhere in the Midwest, I don't think here, that they wanted us to use. So we used that cluster, and for the first time in my career, I did high throughput, truly screening of materials properties for a particular application. So we calculated about 10,000, that was a lot in those days, DFT versions of getting voltage, capacity, and energy density of possible compounds that could replace manganese dioxide, a drop-in replacement. That's really important. If you work with industry, they don't really want to re-engineer everything they do. They want a drop-in replacement, something that's going to make their product better, but not a lot more expensive. So I'll tell you that we were able to find, so we calculated 10,000, we used data-driven statistical methods to expand that space beyond what we had the budget to compute. So this is basically the same as machine learning. So we screened over 100,000 compounds, and as you can see, 1,500 of them did really well on energy, voltage, capacity, and energy density. And those were the three metrics that I thought about first when somebody tells me, get a better cathode. Isn't that what we say? Like you drive your Tesla or your Nissan Leaf or whatever. I just want more range. But if somebody tells you, yeah, I'll give you twice the range, but it's going to blow up every 10th time you go into that car, that's not really a trade-off you're willing to do. The same is true for these guys, that if you add stability to that screening funnel, which in the beginning we didn't know how to do to screen for stability at pH 15, because that's what these little buggers contain. The electrolyte is really highly concentrated KOH. So we learned how to do that, and we added that, and suddenly those 1,500 compounds dropped to 200, and trust me, we were generous on that screening. So the company took the 200 compounds, they went away, they tested a lot, they came back to us a few years later, and they said, we really like this one. We have introduced a few defects. We're working on surface passivation because it kind of gases oxygen, which is very bad at high charge, but we really like it because it's twice as good as what we have, and it will work as a drop-in replacement. It's relatively stable at high molar KOH. And in 2019, I was at the launch in Austin, Texas, where they started to blend in that material into the Duracell, and they call them optimum batteries. And as you can see there, they're up to 200% better. I'm not rich, don't worry. But Duracell is making money on these, which I'm happy to say. This is what made me, it's not going to change the life that we found a better alkaline battery, but this shows me that it can be done. From prediction, not even being live on the bench, like a new material, from prediction to commercialization, it was about 15 years. And that's, it's a long time, but it can be done. Okay, so I came to Berkeley with that excitement, that this should be done, not just as a consulting project, not just for one group. This should be done as much as we can for everybody. Like we should empower every single engineer and scientist with the kind of data that we were producing with that company. So in 2010, I wrote an LDRD, which is what the little internal proposals are at the lab, for the materials project, and we founded it together with some partners, some of my previous partners at MIT, but we anchored it at LBNL because that's when you can hire staff, which is really useful. If you're going to make something with a longevity, you really need to be able to hire staff. And it was supported as one of the 5 first software centers of the MGI, the Materials Genome Initiative, in 2012, and now it's a core program, and it's $3 million a year. And before you say, oh, great, $3 million a year, that's amazing. $3 million a year for the amount of like data that we give to people, the amount of people who come back and say, wow, that's great. I would never have had access to that without that. It is a bargain for the US government, and we should just do more like this. We should share our experiences and our data in a better way to accelerate our research. So these pillars, what we decided to do are the same as when I wrote the proposal in 2011, to accelerate materials discovery, scaling computations as much as computing power we can get our hands on, employ data-driven predictions, that's the machine learning there, and disseminate this for free to the global community. So before I go into the deep dive on the synthesis, which I consider one of the forefronts, we have to do better there, I'm just going to give a nod to the software and data infrastructure, because without that, we wouldn't be doing any of the stuff we're doing. You can have a graduate student running high throughput calculations, but organizing that data, building on it so that next graduate student can do just as well, and to make sure that all of those data points talk to each other and are well organized so that other people can get hold of them, that's a whole endeavor that even I didn't know what I was signing up for when I started this. So here's the software stack of the materials project that are all written in-house. And we started out, PyMatGen is the oldest code. It's from 2011. That's the I/O code, input, output, basically. Fireworks was the next code. That's the workflow manager. And I kid you not, when I was talking to CS people, which we have embedded in our team from the beginning, and I said, we're going to have to write a workflow code because we can't keep track of all these calculations, and we can't have an army of graduate students fixing them all the time. They said, we have oodles of workflow codes. Don't tell me that one of them doesn't work for this. And I go like, no, they don't. We've tested. Because we needed to be able to dynamically reroute calculations talking to an external database, which is in CS world, really bad idea, because they make all of their architectures around completely isolated nodes that don't talk to each other. So we needed to be able to go outside of that and bring back recipes, basically fix the DFT calculations when they're going wrong. So yes, dynamical reroutes of fireworks, custodian, job flow, Atomate. I heard of some students working on it, using them here. That's great. All of those are to produce the data. Then the data building pipelines are the ones that basically organize the data into a database that enables the API to go in and retract that information in a robust way. MP contribs, I'll talk a little bit about that later. That's how you guys can contribute your data back to the materials project and still keep ownership and control over it. Data visualization, that's making sure that somebody who's not an expert on the Schrödinger equation and DFT can still use the data. Engineers, experimentalists. Because in the end, if I just gave you a flat file and say, here's the outcar from VASP, please go ahead, take a look at it, that's not really truly empowering the community. And all of these are open source. Even the website code is open source. And you can also see that the community has now started to organize other kinds of codes around this ecosystem. And that's the brilliance of open source, that you truly, truly not just empower, but also excite other people. I benefited from this in my career. I should be giving something back to all the other students and postdocs. So yes, it is open source. We try to make sure that it's also well maintained, which is the other struggle. So every single commit that gets sort of submitted to the materials project code base is examined by one of our benevolent dictators. It doesn't get merged with the main branch until we have clear documentation and there's been unit tests and they've passed them. That being said, everything breaks all the time. We have weekly meetings with all the software engineers because this is hard. To give you a sense on how complicated the builder structure is and why we need it, it's because as soon as we produce a new data point that needs to be integrated into this machinery, let's say that we calculate some energies, and you can see here, like we have a dielectric builder, we have oxidation states builder, we have piezoelectric builder, magnetic builder. Every single one of those have to now aggregate the data or organize the data on top of the raw calculation. This is the only way to do it systematically. This also means that it is deterministic. So if somebody wants to reproduce this, and we do this every like 2-3 years, we rebuild the entire materials project from the raw data to make sure that nothing is lost, that this is truly provenanced. Some people are also very surprised to hear that we started this in 2011, but there are actually, as far as I know, not a single data point that's left from 2011. DFT changes, it gets better, we get better functionals, we get faster computers, we get better pseudopotentials. We don't want to be obsolete. We don't want to be something that the graduate students say, well, I just recalculated this, and I can't believe I found this old piece of data in the materials project. We try to avoid that, so we've always recalculating things. We find errors. If we find better methods, if we get faster computers to do it more accurately. And we have a deprecation process in place so that the old data doesn't get scrapped. It sits there. It's still available through the API. So if you wrote a paper using materials project version whatever, you can still go back and check to make sure that was correctly done. So here's the sort of ecosystem in a nutshell. We're using workflows to produce the data. We're using builders to build the aggregated data on top of that. We're using mostly NERSC, but also NREL compute to calculate the properties. All of our codes are available on GitHub. Our API today runs mostly through AWS, and our website is available through the API, so it builds on top of the API. We used to do it from Lawrence Berkeley National Laboratory, but it's not set up to be a 24/7 data delivery hub. AWS is. It's now totally available 24/7, which is great. And as was mentioned in the introduction, we have recently been recognized as one of the pure data resources from DOE, which sort of acknowledges that we're trying to go above and beyond common data sort of management expectations. So if you're a graduate student and you arrive in my group and you want to do that, you want to drive that Ferrari and you want to produce, I just want to give you one slide on what it was, sort of what the flow is. The first thing to produce the data is you're going to have to write that workflow in Atomate 2 or something like that to produce that data. And you have to benchmark it against, again, the gold standard. And what is that? That's experimental data, right? So then you go and find those data points in the literature. And you run that workflow for all of those 200, 300 compounds or whatever there is. And if you don't get close enough, the DFT accuracy of those data, of those compounds, you have to go and fix your workflow because you probably picked the wrong numerical parameters. You have to pick them automatically for semiconductors, for metals, for insulators, and that has to be done automatically. So all of those parameters are done. And once you feel like, okay, this is as good as DFT can get, and I did no manual intervention, that's when you've done the best you can. And you go to town and you hear me dragons, right? Now you calculate data points that nobody has seen before. Those are true predictions based on DFT. And if you have enough of that data, then you can do machine learning. So that's the sort of the trajectory. Okay, so that's all that on software infrastructure and a lot of work. What we want to do, accelerated materials, right? And I'm not going to talk too much about the design today, because I feel that today that is becoming more and more everybody sort of like commoditized to some degree. We've seen some truly spectacular materials design exercises just in silico in the last couple of years. I think Facebook and Meta started in 2019, and these guys have more compute than I could ever dream about. They're using their sort of unused clock cycles of their compute to calculate surfaces for catalysts, and they're giving all that data for free, which is great. They've also designed novel catalysts in collaboration with university partners. Google DeepMind in 2023, I think released 2 million calculated compounds, whereof 380,000 were predicted to be new, something that broke the hull with the materials project. And we're in the process of importing all of that and making it available through the materials project. And then Microsoft comes along, again, I think into 2024, using diffusion generative algorithms of not just new structures, but actually also structures with properties. You can see how fast this field is moving. And they're all training this on either materials project data, materials project derived data, or data they produce with materials project algorithms, which is why I somewhat subtle put a little MP inside on all of them, because they are indeed all using things that we hopefully help them sort of leapfrog to this point, but using their expertise and their compute. So we've also designed new materials, and we try to, again, like the Duracell idea, like we take them from predictions all the way to commercial, or like not commercial, but to synthesis and characterization. So here are a few examples in carbon capture, magnetocalorics, thermoelectrics, electrides, piezoelectrics, and photocatalysts. And this is great, right? I love doing design, but I'm going to just highlight how long it took to make these materials once the predictions were there. And I'm not talking about the materials now that we predicted and people tried to make and they couldn't. That's even worse, because when do you tell the graduate student to give up? Trying to make a new compound that's never been made before is truly, truly depressing for that student. So we try not to send them into the lab before we feel pretty certain about it, which again goes to the synthesis aspect, right? Okay, so it took months to make the magnetocaloric ones, months for the thermoelectrics. The photocatalyst was a spectacular example of high throughput experimentation together with computation. So that one, it looks a little odd, 16 compounds, but it was over several years. But the one I like to talk about a little bit is the piezoelectric one. That was this particularly stubborn, wonderful postdoc at NREL who for 2 years was sort of digging into making that particular strontium hafnium oxide and showing that it was new. It was not one of the previously known ones. 2 years. So again, when you tell somebody to give up, I promise you, I did not tell her to keep going for 2 years. She did it. So synthesis, we have to do better, in my opinion. So going back to the little sort of threshold that I talked about at the very beginning, why is it that we can't calculate synthesis? Well, I think it's because we don't have a single equation that governs it. It's not like the Schrödinger equation, which tells you how matter should behave, right? If you have the right atoms in the right places, it tells you what the ground state, and you can derive properties. But synthesis, depending on the method you're using, hydrothermal, solvothermal, shake and bake, epitaxial growth, you have different amounts of thermodynamic and kinetic factors that govern the growth of the material. So it's not one single equation. And therefore, the people who are really good at synthesis, those are the people with a lot of experience. And data is, in that sense, king, right? People are really good. They've seen a lot. They've seen the negatives. They've seen the positives. It truly is a data-driven expertise in that sense. So when we started to feel like, okay, I don't want to send any more graduate students into the lab and have them stand there for 2 years. I want to do better at this. I want to work with them to predict not just what they should make, but also the conditions under which they should make this material. We started thinking about synthesis a few years ago. So here's the first. I'm going to show you 3 things, 3 basic attempts to sort of chip at synthesis a little bit. The first one was, can we just figure out when try not to make something? When is something completely dead in the water, so you don't even think about it? So in order to get to that, we first did ICSD, which contains mostly known experimentally verified structures. So we calculated all of those. We have those in the materials project. And as you can see, the energy above hull, which is very typically used in computations, it tells you how metastable the material is. The higher the energy above hull, the less stable it is, the more incentive there is for that material to decompose into things that are more stable than that. The energy above hull falls off pretty quickly as you, with prevalence, like things that have been seen. So the dark blue columns here are materials that are known, synthesized, and exist in nature, basically at 1 atmosphere. And as you can see, if I were to put a screening criteria, like say, okay, I'm not going to look at anything that is higher than 100 MeV per atom, I do pretty good on oxides. So here we plot the cumulative percentage of compounds. The red curve up there is oxides. If I put my screening criteria at 100 MeV per atom, I get 80% of all known oxides. You could argue that's pretty good. I'm going to miss 20%. That really cool oxide with some cool properties might be missed, but hey, maybe I can live with that. But that same screening criteria for nitrides, I get 50% of all nitrides. So the degree of acceptable metastability is clearly different depending on the chemistry, depending on the anion. So why is that? Can we do better? So we thought about the synthesis process, and here I'm going to say that we are mostly focused on solid state. So solid state synthesis, it's widely used. It's technologically relevant. If you want to make bigger batches of something, solid state synthesis is good. So okay, if you want to make a tantalum nitride, you're starting out with your precursors, tantalum oxide, ammonia. What tells you whether you're going to make that brilliant polymorph with the specific properties that you're after, or if you're just going to make amorphous gunk? Okay, so let's look at the thermodynamics of amorphous gunk versus the possible polymorphs that we're after. So the amorphous gunk is liquid-like, right? It has a higher entropy, configurational entropy, than any of the ordered polymorphs. So the slope of Gibbs free energy with respect to temperature is entropy, so that should have a higher slope. Now, polymorph A that starts out with an enthalpy, so Gibbs free energy at T equals 0, that's higher than the amorphous state, has absolutely no chance of forming. in synthesis. Because you're already breaking the bonds in tantalum oxide and ammonia, you have no kinetic problem of making amorphous gunk. It could just happen by just breaking the bonds at some temperature. So it's kinetically feasible, and it's thermodynamically always going to win over polymorph A. There's no chance for polymorph A. But polymorph B and C, they have a window of opportunity at lower temperatures. After at some point, you are going to try it. You're going to make the liquid or something, depending on when the thing melts. So we hypothesized that a rigorous energy limit for polymorph synthesizability is set by the enthalpy of the analogous amorphous phase. And we can calculate the enthalpy from first principles. So here is a selection of 44 different chemistries or stoichiometries that we calculate the enthalpy of. And as you can see, they vary quite a lot. We've done oxides, sulfides, nitrides. And what you also look at, so the enthalpy is that sort of the bar, the top of all the bars. And you see the little spread that comes from the fact that calculating amorphous state isn't just one number, because you can have different samples of amorphous states. And it varies, right? You're getting all the things from like 100, maybe 70 MeV per atom up to almost an EV per atom, depending on the chemistry. And the open circles are materials in the ICSD that are either hypothetical, they've never been made, or they amorphosize as 1 ATM, so 1 atmosphere. So, and this is what we're running our calculations at. The filled ones are things that do survive, that have been made, polymorphs that have succeeded. And we have not found, not in these 44 systems or anything we've calculated since, a single system where the amorphous limit is violated. And the coolest thing about it, in my opinion, is that it really tells you something. So in the boron oxide case, it's a very low amorphous limit. Because boron oxide, as soon as it can form these little tetrahedra or whatever, it doesn't really care if it's amorphosizes over that. Long-range interaction doesn't matter much. But boron nitride loves these covalent, very organized things. So the amorphous energy is very high. And that gives you, the high amorphous energy gives you an opportunity for metastability. Now you can design new kinds of polymorphs within that window. So that's where you see a lot more possibilities within boron nitride as compared to boron oxide. And that goes back to the higher amount of metastability in nitrides. And of course, what's the skyscraper? For those who can see on the plot. Yeah, I mean, we've had 2 Nobel Prizes already, right? There's 3 by now, buckyball and graphene. There is a reason we can make any nanocarbon tube out of the wazoo, because the amorphous state is so unstable. It gives a huge opportunity for metastability, because it doesn't compete with all these polymorphs. So, and for screening, this is better, because now we don't have one model fits all, not 100 MeV. So that's great. Okay, it's the beginning. If your functional polymorph is higher than the amorphous analogous state and enthalpy, don't go there. Don't even try. And while for many of them, maybe you can see that, it's pretty high, but I got to say, in the silicon dioxide, it does screen out a lot of very unstable zeolites and things. So it can be useful. Okay. And we call it the metastability skyline. And this is, I don't know, does anyone recognize it? It's Chicago. Yes, because the first author was from Chicago. Okay, that was the first attempt. The second attempt was, okay, let's do a little bit better. See, can we use thermodynamics, because that's what we have mostly in the materials project. Can we use thermodynamics to get ideas about precursors and reaction pathways? And here's where, graph neural networks, fantastic. We can literally design a graph neural network to track the reaction energies based on the materials project from whatever precursors you ask for and anything beyond. So in the lithium manganese oxide and the manganese and sodium oxide cases, if you allow any metathesis, anything with spectator ions, any reaction to happen, you get a fair amount of reactions. And if you assign scoring functions to them, you can now select which ones have a larger trajectory down in delta G. So they are more sort of reasonable guesses for making a good amount of material with a low amount of impurities. So we've tested these kinds of what I would call like thermodynamic-based reaction network kinds of things, and they're not bad. Typically, the top-ranked 3 ones usually contain the one we see in experiments, but what we've also found is that we are lacking something. We're lacking, in this case, we're lacking any kind of spatial information, temporal information, and we certainly have 0 kinetics, except for what comes directly from thermodynamics. We've seen that it nicely correlates with targets, with impurities and precursors, but we really have to do better. So I'm excited to say that you are going to be the first ones that I show these slides for in terms of building kinetic information into solid state synthesis, because my student submitted the paper yesterday. So we built first a cellular automaton, which is a very, very simple way, but it's flexible. It just basically looks at the neighbors of a grid of points, basically cellular states. And then it has a scoring function to look at, should I react with B, should I not react with B, based on whatever you tell it to do. And the first version of the cellular automaton, we just built in thermodynamics. We just looked at the reaction energies, and we had Hammond's rule for some amount of fluidity. And then you let this thing go, and I think I can show one example of how it evolves. So it's basically an evolution cube, which changes the state of each cell depending on some scoring function where you can build in thermodynamics or kinetics if you have it. So in the first version, we only had thermodynamics. In the second version, we go like, okay, and this is the one this is the first time we're showing these things. So a lot of credits should go to Veer Karan, who is my graduate student back at Berkeley. How do you build in kinetics generally in solid state synthesis? Well, we took the hypothesis, and again, this is how we do it, right? Of, okay, you have an interface of two solid state materials, so precursors, and you want to ask your sort of, like, what are the scoring functions for forming different target phases? We hypothesized that at that interface, so if you see, like, basically something, in order for something to nucleate with a certain stoichiometry, you have to have good transport of the right amount of each of the ions to that interface. And that interface could be approximated as the amorphous version, because you can imagine that when things are moving around, it can't be completely crystalline, right, of that stoichiometry. So that's our hypothesis. Relative kinetics should be captured in the amorphous liquid-like reaction layer with the same stoichiometry as the target phase. Let's see if that works. So we have our convex hull, and we took barium titanate because that is a really challenging system from the perspective of thermodynamics. It has a bunch of phases that are incredibly close to each other in energy. So by thermodynamics alone, this does not explain solid-state synthesis reaction outcomes. And then we calculated the rigorous Onsager transport coefficients, which includes all the correlations between ions moving. You have to do that in solid state. Oops, was that me? I'm going to stay away from that. In all the different phases and their amorphous analogs. We incorporate that information together with the thermodynamics in the cellular automaton, and we tracked what was made as a function of reaction coordinate or time. And here you can see the results with diffusion and without diffusion and what difference it makes. So it's the same thermodynamics, but we're adding this kinetics from the amorphous version for each phase. And I cannot tell you, I can't say, so the problem is that, of course, the experiments don't have these curves, but they do have text describing what is made at different times. And the impurity phases are exactly the same. The majority phases at the end of whatever the simulation as a function of temperature is exactly the same. The amount of the impurity phase is also the same, and the consumption of the impurity phases in favor of other phases is the same. So for example, they see the 2,1,4 barium titanate phase appear first. They see the barium Ti2O5 phase appear after that. And they see the barium titanate phase grow as the majority phase with those two impurities at the end. And the other one, that's another experiment, another group that we compare them to. So we have different precursors. The major final product is the 2,9,20 phase, which we don't get by only thermodynamics. It has to include kinetics in order to get that. And we get exactly the right growth of the impurity phases. So I do think that we're onto something here, and I'm very excited that this is, as far as I know, first principles-based kinetics and thermodynamics predicting of solid-state synthesis. Okay, I don't know how I'm doing on time. Oh, good, because I only have a few slides left. Fantastic. Then I don't have to talk more. I can just. Okay, so I'm just going to add with what is sort of the impact on the community at large. So the impact of the fourth paradigm, right? The data-driven. The materials project, this is what it looks like. Hopefully you're all using it. The more you use it, the happier we are, because that is truly leveraging other people's knowledge directly. To give you some examples, the elastic tensor data set that we calculated many years ago and we keep adding to and refining and doing better is being used in a lot of machine learning. For example, here's one JAX paper that learned bulk modulus and shear modulus from that data and predicted super hard codings, and they made them and they tested them. So again, an acceleration of their work from using our data. Similarly, the same data was used for machine learning the Dubai temperatures and getting photo phosphor hosts that then again were synthesized and tested, and that became in Nature Communications. And we have nothing to do, by the way, with these other papers. That's just them taking our data, doing awesome, incredible stuff with it, and predicting new materials. I've had a conversation with a few of you today, and somebody asked me, how do you know which data to store? Do you store everything? That's really hard. By the way, wave functions are huge. So one thing that we stored, but we had no idea of the impact at the time we made that decision, is the relaxation trajectories of all of our calculations. We stored them simply because we wanted to build faith in that our calculations were well done. But some really clever people, and this is 10 years of those relaxation trajectories, a lot of atomic forces and energies pairs. Some smart people went, I can fit a potential to that. And then run DFT accuracy simulations in lamps for much longer. And we had a lot of that data. I was just sitting around. And here comes the rise of the interatomic machine learning potentials. Without that decision, that would have taken a lot longer, because most of the DFT databases that started out around the MGI, as far as I know, all of them except the materials project, did not save the trajectories. So we wouldn't have had that ability. So everything from the early works of Tan Xie, Chi Chen, up until the Maze Foundation model that I think is still in archive and being reviewed, are all trained on the materials project, 10 years worth of trajectories. We're excited to not just build our own data into different apps, but also incorporate other people's. So when people come to us with a fantastic data set, and if we feel like this is really it, we should work with you. We try to work with them to develop a new app. The more help you can give us, the better, because I really only have 4 software engineers. So the Moth Explorer, the Catalysis Explorer, and the Synthesis Explorer are all due to other people's work that are now being leveraged and disseminated through the project. We focused a lot on properties and not just on structures, so that people can do machine learning on not just structures. Structures are important. They're the bread and butter, but properties are what we need to really design. So instead of just blanketing space and structures, which I think other people are better at anyway, we've paid a lot of attention to materials properties. It is a very data-hungry world. I think I can speak for a lot of the people in also the sort of the open AI people. They are so data-hungry that you can see the rise of machine learning in the citation of the materials project. So we are on average cited 5 times per day in papers, and about 2 of them are on machine learning, and it's rapidly rising. So this is really timely. And as we've noticed, we're one of the 7 Office of Science blessed data centers. We're hoping that we're democratizing materials data. We have now, I think the last number is 575,000 registered users, 450 people register new every day, and we're serving only over 178 countries, including some countries which don't have the same kind of access to journals that we take for granted. And I live in California. We were out a lot of journals for a while, so I know how painful it is. And with that, I really want to thank my 4 staff at LBNL, all of you all for listening, and the entire community, and I hope we can do this all better. And I'm happy to take any questions.
So I'm going to play role of chief question wrangler for a moment. And we have people with microphones. So if you ask a question, you actually have to use the microphones. So with that, questions for Dr. Persson. Before the panel, there will be a panel after this. So if you don't get to ask the next 5 minutes, wait 5 more minutes, then we'll have more time. And the first one's always really scary. First question, 2025, will be.
Yes.
Okay, what fantastic work. Yeah, I have a question. I'm working on like fuel cells, electrolysis research, but this close to commercialization, that catalysts have been optimized years and years. But that's how to use your approach to optimize that catalyst. Do you have any idea?
To optimize the catalyst to reach commercialization.
Close, like this,
Close.
the fuel cells, electrolysis development have been decades and decades. That's a highly optimized catalyst already.
Yeah, they
How
are.
to your data science play a role on this part?
That's a good question. And I think for every field, and this is what we experienced with the Duracell project too, right? You have to work really closely with a company to know what they can do or what you can do. So what I found is that things that engineers do a lot better, you shouldn't even try to do, right? Because that's something that they're already on top of. But things that they find a hard way of doing, for example, screening small additions of things to that catalyst. If that's something that's easy to do computationally, if you have the merit function that you're looking for, like an absorption energy, something that you can cast into an energy, something that can be calculated, that is something that we can span a large sort of space in optimization from a computational perspective. But maybe when it comes to, then we have to drop that catalyst into environment, you can screen for dissolution, but knowing exactly what's on the passivation layer, if there is one on the catalyst or something that involves on the surface, that's much harder to do today. Might get better. So I suggest that the optimization, we worked with that company for many years, right? Even when past 2005, they came back to us a few times with questions. We kept working with them. So I do think that close relationship is important and using the best of both worlds. What can they do really fast? What can you do? So I know that it's pretty general, but every system needs their own kind of decisions of what you can do. So catalysis is one thing, batteries is another one. I would probably go for chemistry optimizations, like of the actual surface. Small nanoparticles, right? Yeah.
Okay, so I'll go ahead and ask a question. And this would be something that I'll get out of the way of the mic.
Can you guys hear?
Can you guys hear or not?
Okay, good.
Okay. So you mentioned the number of users from around the country. Do you see any differences in how people are using it based on where they're at?
Okay, so first of all, we have a privacy policy. We never associate a particular user with a particular search, but we can do aggregates of sort of like to improve the ability of the project to meet the needs of our users. So we look at, for example, if people click here, do they give up right away? So those kinds of like user experience surveys we do, but we never look at specific searches. And even though clearly some people think we might do industrial reverse espionage. I mean, we could, right? Hey, you're from Samsung. Oh, what element are you looking at?
So I didn't actually think that. But okay.
Oh yeah, I've been asked that. And some companies don't allow their people to use the materials project, but some of them use it at home with their Gmail.
So along similar lines, you mentioned that part of this is democratizing access. Do you have stats of usage of materials project in R1s, R2s, R3s, emerging research institutions?
So good. We don't, but we certainly could get it. We could. I think I wish I had somebody who was full time to do those kinds of surveys. My 4 software engineers are mostly just fixing bugs and including more data. But that kind of data would be really cool to have. Occasionally we get stories. People contact us out of the sort of blue, and those are the ones I can share because that's kind of, so when our Probay analysis app went down because of usage before AWS, before we were a little bit more sort of industrially, I got an email from some people doing water purification in Australia, and they were really mad at me saying like, no, you can't be down, we need you. So that's how I know that they're using dissolution diagrams in Australia for water purification. I had no idea. I have a guy in Nigeria that has no access to journals whatsoever. So when he publishes, he uses the MPID of every single compound he talks about. So those are the kinds of stories. But no, I don't have good data for you in terms of that. I wish I did. Hey, we have...
So you talked about some of the machine learning force fields that are being developed on this database.
Yep.
And you also talked about a lot of predictions or calculations you've done on amorphous data. And is there an availability to combine both the structures that are around equilibrium, like the relaxation data, with a lot of the amorphous data? Because that could help. A lot of these universal force fields are good at relaxation, but probably struggle at like dynamics. So can you speak about making that data available?
Wonderful question, and you know what you're talking about. Yes, I'll be happy to tell you that as of last week, we published a paper in November on amorphous materials that includes all the amorphous stuff. So we basically made an amorphous database. Yes, we saved all the trajectories. Yes, they're now available as of last week.
Thank you.
Yeah, you're very welcome. So there is an S3 bucket on AWS that you can use. And if you contact me, I don't know if they have announced it directly on the Materials Project yet, but if they haven't and you want it earlier than everybody else, send me an email. I'll send you the link.
Let's go for it, Paul. Okay. How about we do one more question before we do our handoff and for panel? So, great.
Thank you. Great talk. So my question is, you mentioned that industry partners, or whether or not they're partners, companies like Microsoft and Google, are throwing massive computational resources at these problems.
Yep.
What do you see as kind of the edge or angle for academic institutions to compete against this with less resources?
Yeah, so that's also a great question. I have been asked that before. What chance do we possibly have with like a 10th or a 100th of their compute? Well, they are still using the 10 years of development and workflows and the parameter space that we are constantly evolving in the Materials Project. So I do think we have a very significant role in play in like helping them to choose things that are very, very well established and benchmarked from a domain expertise perspective. So the people that I love working with, but they're not always the people who end up doing this at companies, are truly interdisciplinary people. People who have a material science background, but an interest in CS and software. In these companies, most of the people I end up interacting with are pure CS people. So they rely on us to tell them what actually works and what doesn't work in the material science domain. So I think that, and that goes back to an educational perspective too. Our education is too streamlined most of the time, right? So these people are rare, the ones who end up going and taking CS classes on top of everything else they're doing. So I do think that that's a valuable one. In the end, is Microsoft and Google and Meta going to develop new materials for all the problems we have in the world? Most likely not, right? They're going to develop machine learning boxes that work, that you want to run on their Azure cloud, because that's how they make money, or the Google cloud, right? And then they're going to leave the actual hard work of doing the materials development to other people. That's my guess. I could be wrong. Please prove me wrong, Google and Meta and Facebook, because that would be wonderful. So I am pretty sure we will have a lot of things left to do.